ครับตอนนี้ก็ขอต้อนรับวิทยากรนะครับ We welcome Professor Nicolaas Bloembergen. Ladies and gentlemen, welcome to a special seminar on laser technology in peace and war. First of all, I would like to invite the Vice President of Prince of Songkla University for Outreach and International, Associate Professor Supachok Riyakoson for opening speech.
Professor Bloembergen, President Prasad Dean Thawat, Director of Government Affairs UNOCAL, and Director of Event Coordination, International Peace Foundation. Distinguished guests, ladies and gentlemen. First of all, I would like to extend a warm welcome to our honorable guest speaker, Professor Nicolaas Bloembergen, and thank all audience in attending a special lecture today. May I express my sincere appreciation to the International Peace Foundation for giving us a privilege and great chance to host these auspicious occasions. I feel highly honored to have the Nobel Prize Laureate visit to Prince of Songkla University. From the topic of laser technology in peace and war, I am quite confident that all the audience will gain profound knowledge and be proud of sharing time with the experienced speaker today. I believe that the lecture will bring us friendship between the two countries and universities and will be even more meaningful and fruitful. May I now invite all of you to join the special lecture by Professor Nicolaas Bloembergen. Thank you.
Thank you very much for your kind introduction.
Excuse me. Before we start the seminar, I would like to invite Mr. Janis Hachuen for a special speech on behalf of International Peace Foundation. Thank you.
Chairman of the International Peace Foundation, who unfortunately cannot be here today, but who expresses his best wishes to all of you. So, ladies and gentlemen, dear friends, I have no concept for peace and no solution how to achieve peace, but I know that the first step towards peace is dialogue, and the first step towards dialogue is respect. The International Peace Foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue where people who normally don't meet, people from all walks of life, people who speak different languages, even if they use the same, As politicians speak another language than artists and business and religious people, another than scientists, it is seldom that they speak with each other or even work together. We live in a world where some people pretend to know the answer and solutions, how to solve problems, how to achieve peace. Thought the quest for peace lies in the art to pose the right questions. Peace is a process, dialogue is a process. It is nothing which is achieved instantly, it needs time. This is why Bridges is not organized as a single conference and then everything is over again and forgotten, but as a series of events over the period of 1 year in which 24 Nobel Laureates for peace, chemistry, medicine, literature and economy built bridges with Thai leaders in all parts of society and with the general public. After the first 20 events of Bridges, which attracted 8,000 participants in November alone, we have been approached especially by students and young people who have been inspired by the content of the events and who want to actively participate in this dialogue process towards peace, which is not something which can be left to the elite of a few, but which needs the participation of everyone. This is why we want to further encourage your input and support, and why we look forward to your questions and suggestions, your advice and guidance in this dialogue process towards peace. I thank the chairman of the Thai Advisory Board for the event series Bridges, His Excellency Anand Panyaranchun, Professor Prasert Chittapong, Professor Supachok Viryakusol, Mr. Vichai Taranya Chester from UNICEL, who is one of our major sponsors for Bridges, and of course the Prince of Songkla University, and all sponsors and partners for our fruitful cooperation, and especially Professor Nicolaas Bloembergen, who came to Thailand without any honorarium to support the events, and I now look forward to his keynote speech and his important contribution to build bridges. Thank you very much.
Thank you very much. And before we move on, I would like to present a brief introduction of Professor Nicolaas Bloembergen. Professor Nicolaas Bloembergen is a professor for physics who received the Nobel Prize for Physics for his contribution to the development of laser spectroscopy in 1981. He was born in the Netherlands in 1920, studied at the University of Utrecht, and obtained the PhD degree in 1943. After the Second World War, he came to America and started to work at Harvard University in the field of nuclear and electron paramagnetic resonance, later in quantum electronics, microwave lasers, nonlinear optics, of which he is one of the founders, and lasers. This started a lifelong association with Harvard, which continues to the present day. In 1948, Nicolaas Bloembergen returned briefly to Holland to receive the PhD degree from the University of Leiden for his thesis on nuclear magnetic relaxation, which became the classic Bloembergen Pound and Purcell paper, or BPP, in the Physical Review of 1949. Professor Bloembergen received various awards, such as the Medal of Honor from IEEE in 1983 for the invention of the three-level maser, and he is a member of numerous professional societies. Until present, he is Professor Emeritus at Harvard University, and since 2001, Professor at the Optical Sciences Center at the University of Arizona. Ladies and gentlemen, please welcome Professor Nicolaas Bloembergen.
Thank you very much, and good afternoon, ladies and gentlemen. I think I'll take my jacket off. It's pretty warm up here. The word laser is based on the English language. It's called an acronym because it uses the first letter of five English words. L stands for light, A, amplification, S for stimulated, E for emission, and R for radiation. And so it is a light amplifier based on stimulated emission of radiation. The interesting thing is that the word laser is used in many other languages, and including the Russian language. The Russians talked about a laser, they called it laser, in 1962. And this was at the height of the Cold War between the Soviet Union and the United States. But among the scientists, they communicated, and they used the same words, and even although the countries were on opposite ends, the scientists had many stimulating discussions on this subject matter. So science, in many cases, is a universal language. I'd like to start with a little bit of physics to justify the use of stimulated emission and what it stands for. But then the main object of my talk is to introduce you to the various applications of lasers. So if you will bear with me for a little bit of physics, may I have the first slide projected? And is the machine on, the light bulb? Yeah, I hope this is visible enough. As you know, light gets, I need this as a pointer, I think. Yeah, works. That's a laser, incidentally. And light is produced by electrons circling around the nucleus in an atom or in a molecular orbital. And when they are in a orbit is higher energy, they can fall down to a lower energy, and the energy difference between the two orbitals is emitted as electromagnetic radiation. And here you see another one. Here the energy difference is larger, then the light that comes out has a higher frequency. And all light sources before lasers were based on this spontaneous emission. Now, the next slide, why doesn't, should go. It works. Most substances are absorbing light rather than emitting light, because unless they are at a high temperature, the electrons are in an orbit of the lowest energy, and all they can do is increase their energy by the absorption of a photon, a light quantum, out of the incident wave, and of course then the incident wave gets attenuated, and so most materials are absorbing. To get stimulated emission is the inverse process of absorption. The electron is prepared already in the orbit with the higher energy, and then it gets tickled by the incident light wave to add another photon, and then you see that you get amplification of light. Now, the essential requirement is that you have more electrons in this orbit of higher energy than in that orbit of lower energy, so that the stimulated emission processes dominate over the absorption. And if you have a material in thermal equilibrium, that never happens. You always have more electrons in the orbital with lower energy than in the higher energy. So you have to do a trick. You have to pump the material to get dominated stimulated emission. May I have the next slide? And this is how it is done. You take a system with more than two energy levels, and you pump the material up by absorption to that state. And then you get more electrons in that energy level, that orbital, than in this intermediate one, which you bypassed. And then you get stimulated emission or useful laser output at this transition indicated there. And that is the idea behind laser action. May I have the next slide? And here you see an actual energy level diagram of chromium ions in ruby. And this material was the first laser material. And Mayman operated the first laser with a ruby in 1960. The pumping mechanism here is at microwaves, and that is called the maser for microwave amplifier by stimulated emission of radiation. But then you see there is a break in the energy scale, and here we are suddenly at energies 10,000 times higher than these microwave energies. And then we are in visible light, and not talking about microwaves anymore, but the idea is the same. You pump it up with a hot photographic light bulb flash lamp to these levels. They fall down to these fluorescent levels here, and then you get the useful laser output at this wavelength, which is red light. The next slide shows the difference between light from stimulated emission, which is coherent, and light from spontaneous emission. And this is a crowd in a fairground or at a marketplace, and people walk in all different directions and talk in all different directions and emit heat in all different directions. But this is a military column or sports parade, and everybody walks in step. And that is what these atoms do, which get forced in step by the incident light wave, and they amplify that. They only want to contribute more to that light wave rather than to spontaneous emission in other directions. And so you get a coherent synchronism between all the atoms or molecules, and all contributing to light emitted in one particular direction. Next slide shows this indicated. Suppose that this is a piece of ruby, and you have two mirrors reflecting surfaces put at the end. Initially, the atoms are emit spontaneously, but then pretty soon the light that gets emitted normal to the mirrors gets dominant, because they get reflected and they stimulate the atoms all to emit in this direction. And you see you get this exponentially growing light wave, and then you make one of the mirrors slightly transparent, so you have a useful output of the light pulse. Next slide shows you how simple the first laser is. You see all the elements are here. Here is the ruby crystal with a totally reflecting mirror there and a partially transmitting mirror here. So you can get a useful light output. And then the pump is provided by this photographic flash lamp, a high pressure xenon flash tube, which pumps up these chromium ions in the ruby according to the energy scheme I just showed previously. And why are people so excited about this? Because this laser light is now different in three important characteristics from ordinary light sources. May I have the next slide? This is another laser. This is a second type of laser. There are thousands of lasers now. This is a helium neon laser. And here you do the pumping by making an electrical discharge in this gas mixture. But the ideas are otherwise very similar. Next slide shows you the laser characteristics. All the light comes out at one very particular frequency, which is defined by the difference in energy levels that get stimulated. And in fact, this can be so precise that you can measure the frequency of light in appropriate cases to 1 part in 14 decimal places. And such lasers now will become new atomic clocks and will be new time standards to 1 part in 10 to the 15th. This is not yet universally accepted, but that is the future. But we won't talk much about that because that is a scientific application, and we talk mostly about practical applications. Of course, the directionality of light you see demonstrated by this laser pointer. But the light is so directed that it is, we say, diffraction limited. And that means that the angle of opening is the light wavelength, which is about 1 micron or a millionth of a meter. And if you now had a diameter d of a meter mirror for this laser, then you see this light angle is only 10 to the minus 6, 1 millionth of a radian. And that means that if you had a telescope here with a 1 meter mirror and you shine that laser light to the moon, the area you illuminate on the moon is like a football field. About 100 meters, a spot for 100 meters, that's all. It's the distance to the moon times 1 millionth. And so on the moon, you illuminate a size of the football field. And the astronauts in the early 70s put in retro-reflecting prisms on the moon, and then they pointed the laser at it, and the laser pulse came back down, and they measured the time it took for the light pulse from the ruby laser to get out there and back. And they could measure that so precisely that they know the distance between their telescope and the spot on the moon to 1 centimeter. And you say, who cares? And then somebody in Japan did the same thing. And again, who cares? But then you get triangulation, and then you know the distance between this point in the US and that point in Japan to 1 centimeter. And you can say, again, who cares? But then you repeat that same measurement a year later. And then you find that that distance between the Asian continent and the American continent has changed by a few centimeters. And that is very important, because that gives you a lot of geophysical insight and of the upwelling of materials in the center of the Pacific Ocean, also the center of the land, and how the tectonic plates of these continents move apart. So that is real important science. Now, because of the coherence of light and the diffraction limit, you can concentrate the light by focusing it. In fact, you could concentrate it on a spot size of lambda, the optical wavelength, which is about 1 micron. That's a millionth of a meter. Very small spot. And as you concentrate the energy, you get very high intensities. But here we don't push things that far. I take a pulse of maybe 10 picosecond duration, 10 to the minus 11 seconds. Has only a very tiny amount of energy in it, a millijoule. Now, to give you an idea of how much a joule of energy is, a light bulb of 100 watts consumes 100 joules in 1 second. So a millijoule is 100,000th of that, and it's what a 100-watt light bulb consumes in 100,000th of a second. So it's really a very tiny amount of energy. But look what happens when you have that amount of energy in that short a time and concentrate it on, I don't focus as hard as I could. I focus to 100 lambda, 100 microns. Then you illuminate an area of 10 to the minus 4. And then you see that with this little calculation, that the intensity of the light in that spot for that short a time corresponds to 10 to the 12 watts per square centimeter. Now 10 to the 12 watts is a lot of power. In fact, it's equal to all the power generated by all electric generating stations on this earth. And imagine all that power concentrated to 1 square centimeter. And you guessed it, all hell breaks loose. Every material gets transformed into plasma, evaporates, and one can produce stellar-like conditions on Earth in the laboratory by concentrating the light in space and time. Next slide. Gives you an idea what this means. You know, here is the sun and the Venus and no clouds. You feel uncomfortably warm. But you only get irradiated by the sun at a rate of 0.14 watts per square centimeter. 40/100ths of a watt. And that makes you already very uncomfortable. At the surface of the sun, you have black body radiation corresponding to 6,000 degrees Kelvin. And that corresponds to 10 kilowatts per square centimeter. But we are talking 8 orders of magnitude more, terawatt, 10 to the 12 watts. And if you go a little further still, which is achievable, you get black body radiation corresponding to 6 million degrees. And that is what happens in the interior of stars. And just by concentrating laser light in time and space, you can produce these stellar-like conditions in the laboratory, albeit for a very short time and in a very small volume. Next slide shows you that the light intensities, we now back off. We don't evaporate the material, but we take a crystal like shown here called potassium dihydrogen phosphate. Doesn't matter what it is much. And because the intensity of the light is so high, the electrons start to behave like what happens to sound in an organ pipe if you push the air too hard, or you have a string instrument and you play too loud, you get harmonic distortion. And what happens is that the electron vibrations get pushed so hard that you get the harmonic of light. And here you see that the red light of the ruby laser is changed to the blue, or really close, near ultraviolet light by this crystal. And this is called second harmonic generation of light. It is a prime example of nonlinear optics. And 2 red photons are converted by this crystal into 1 blue photon of twice the energy, twice the frequency. And there are hundreds of phenomena, so-called nonlinear optical phenomena, discovered because of the optical properties of materials at high light intensities. Next slide shows you, if you take this ruby pulse, this was done in 1961, I think, the year after the laser was invented. You take a lens objective, a 5 centimeter focal length, you focus it in air. You get a spark. Because the light intensity is so high, you immediately ionize the air. In fact, this photograph, a slide I got from a Dr. Terhune, who worked at the Ford Motor Company research laboratories in Dearborn, Michigan. And he says, this is the most expensive spark plug in automotive history. And lasers have never been used as spark plugs in cars, but it shows you the possibilities. And the next slide shows you that in those early days, people were so interested to happen the strength of the ruby laser that they pierced through Gillette blades. And here they say wow, 5 Gillettes. My laser pulse is so strong, so it can pierce through 5 Gillette blades. Of course, we now express it more quantitatively in watts per square centimeter and what happens. But you can really drill holes in any metallic wall. Next slide. And this didn't escape the attention of the military, and there was proposed to use laser beams to shoot down intercontinental missiles. You know, very nice projectile because it travels at the speed of light, and if you have enough energy in it, you could destroy a missile cone even. But, and they call that the incredible laser in the newspapers and the magazines. And then it says here, for credible lasers, see inside, because these lasers still don't exist. It turns out, I was on a committee in '61, and I learned, that was of course then classified information, that you needed 1 million joules to do harm to a intercontinental missile. And I made a quick calculation. I said, if one little ruby, 1 cubic centimeter gives me 1 joule, 1 million cubic centimeters, that is 1 cubic meter of neodymium glass, could give me 1 million joules. But nature is not that simple. To control those very high intensities, you have to do very elaborate arrangements. And people have now made in Lawrence Livermore lab 1 million joule pulses. But you need a whole building much larger than the building we are in to achieve that. And then you still cannot send them out into space. So it turns out that this military dream is still not materialized even today. And that, in fact, most of the applications of lasers have not been military, but have been beneficial to mankind. In fact, the laser market in the year 2000 amounted to $6 billion US. And more than 80% of that was for civilian purposes. That's the main message of this talk, but let's now look, next slide, of some practical applications. The first one is pretty simple and straightforward. You use a laser pointer in the construction industry here to align a tunnel under the San Francisco Bay Bridge for the new subway system. And the next slide shows the little red spot of a helium neon laser on downtown San Francisco to align that tunnel segment. But since 1970, every major pipeline, every gas line, all the horizontals and verticals of all the big buildings that go up in Bangkok and elsewhere are aligned by means of laser beams. Very widespread use. Next slide shows you another thing which is related to the fact that the light is diffraction limited and can be focused on about the size of a micron. And I hope you can see these little dimples in the slide. There's a dimension of 1 micron by half a micron. They were written in by a laser beam, from an argon ion laser in this case, onto a surface that had a photoresist material. And then the parts where the photoresist was affected by the light pulse, you can give a chemical treatment and you can make a little dimple of that size. And then you can say, wherever I have a dimple and I had the light pulse, that is a bit of information, that is 1, and where I have no light, it's 0. So you can write bits with light onto a CD disc. And how do you read it out? By an even tinier laser, tinier than the one I have here, a little semiconductor laser that is in each one of your CD players to read these little dimples. And then it's a very simple calculation to see how many of these bits you can put, next slide, on a CD disk. You just take the area of the disk and you can put it easily 10 to the 10th, 10,000 times million bits on a CD. In fact, with the high resolution disks, you can put 4 times more because you use half the wavelengths, so your little bit dimples get even smaller. And you can get close to 10 to the 11 bits of information on a CD disk. And that's a lot of information. Next slide shows you that on one CD disk you can put the whole Encyclopedia Britannica. Optically stored and optically readable, thanks to the laser. And now we go to the problem of sending that information on the disk, not only by listening to it in your home, but sending it elsewhere in the world. And that gets us to the problem of optical, fiber optical communication. Next slide. Clearly, because you can focus so strongly, you can focus it into a tiny fiber of maybe 10 microns across. To give you an idea, human hair is 30 microns across. So this optical fiber is thinner than a human hair, quite a bit thinner. And people have been able to manufacture glass that's very transparent, but the light is confined by total internal reflection because the index of refraction in the center is higher than at the edges. And then they purified the glass in the last decades so much that you can send that light over hundreds of kilometers before it gets attenuated by maybe 10 or 20 dBs. But that doesn't matter. Now you can build into the fiber erbium ions. They act in a similar way as the chromium ions. Erbium ions of rare earth have lots of energy levels, and you can pump them and you can amplify the light in the fiber by some of these sections that have pumped erbium ions in there. And so you don't even have to reconvert the light back to electronics and amplify that. No, you amplify it as the light travels in the fiber. And now these fibers span 10,000 kilometers or more, and they are at the bottom of the Pacific and at the bottom of the Atlantic. And that is how information gets transported between any 2 points on this globe. Next slide shows you some historical examples. This was the first optical fiber in the streets of Chicago in 1972 to just connect 2 telephone exchanges. Next slide shows 8 years later the route miles that were in operation in the United States. But similar things happened in Japan and in Brazil and so on. Now the next slide shows the first sub-Atlantic cable operation to make a connection between the United States and England and France. And here you see a substation where the light pulses were converted back to electronics and amplified and then back to light. And now we don't need these intermediate stations anymore, thanks to the erbium-doped fiber sections. Next slide shows you the routing of this first transoceanic optical connection. The next slide shows you how the market of optical fibers increased very rapidly, and it's now up there. And in fact, it overshoot part of the problem of the last few years of a downturn in high-tech optoelectronics is due to the enormous effectiveness of these optical fibers. Let me quote, there is a cable system that connects Southeast Asia, including Thailand, with Western Europe. And the characteristics of that system are as follows. I think I have it somewhere here. Yeah. That system is a distance of 11,000 kilometers. 11,000 kilometers. The total cable length, because there are many branches and so on, is 39,000 kilometers of optical fiber. There are 40 landing points in 34 countries, and it only has 2 optical fiber pairs, 2 of these tiny fibers I talked about. And each of these fibers has a capacity of 20 gigabits per second. That is 2 times 10 to the 10 bits per second. So essentially the content of a CD could be sent in a second over that system. But the present, and that system has been in operation since 1999 and has functioned very reliably. There is another system which is called the FLAG Atlantic. FLAG stands for Fiber Link Around Globe. FLAG, Fiber Link Around Globe. That system has 6 fiber pairs. It uses a technical process which is called wavelength division multiplexing, so that in one fiber you can have 40 simultaneous signals going in, because they work at slightly different wavelengths, and then you have to demultiplex them again. This system cost $1.6 billion US. It took 27 months to lay. There were 5 cable laying ships, and there were 4,000 government and industrial organization permits required to put that system in place. 4,000 permits. But it works, and that system has a capacity of 2.4 terawatts. That means 2.4 times 10 to the 12 bits per second. So on that system, you could transmit the Encyclopedia Britannica in a hundredth of a second, if that were ever needed. The system can transmit simultaneously 200 million telephone conversations. Or it could transmit 450 simultaneous high-definition TV films. And that shows you the global capacity of the optical fiber networks, which really has made our system a much more closely connected community. And that is why you can plug into the internet and get the WW information and receive your email from friends in other continents. Next slide. Yeah, let's now go to more high power laser. This is more than 30 years old. This is a CO2 laser, which are not used for the precision. They work in the infrared at 10 micron wavelengths, but they have a very large CW power. In fact, this picture shows the whole laser are these gas tubes. These big things you see are just pumps to pump around the gas, which you have to do because otherwise everything would melt. So to keep the laser substance cooled in a way, you have to have these big pumps. But here is the laser, and it puts out a beam of 5 kilowatts of electromagnetic radiation. And you could focus it, and with 5 kilowatts on a smaller area, you can things that cut metals and so on. The next slide. And such lasers are used in the automotive and shipbuilding industry to drill holes in the 1-inch thick metal plates, to weld plates together, etc., etc. But next slide shows you a little more sophisticated thing. And that is, you want the cylinders in your car engine and elsewhere to have a very hard surface so that they don't wear out. In the old times that was done by heating the whole cylinder mass and then dumping it into cold water. And then certainly the surface got hard, but also the whole wall got hard and brittle. And that is not desirable. What you want in a mechanical workpiece, piece of gearing, you want a very hard surface, but you want the interior of the gears to remain tough. So you don't want to heat those. And that is just what a laser beam that you scan around does. It locally melts a very small surface layer, which after the light pulse has passed, immediately cools off by heat conduction to the bulk of the wall. And so you can quench the surface and make it very hard on a metal piece of any shape, any gear, so on. Very widespread use in mechanical engineering industry. Next slide. Here you see another industrial application. This is the tip of a turbine blade, of a jet engine. These turbine blades are made of single crystal titanium. Titanium is a material that keeps its strength to very high temperature. But the tip in a jet engine gets so hot that what limits the power of the jet engine is the temperature at the tip. And in order to keep that a little lower, what people do with a laser beam, drill cooling holes through the very near the edge of the tip. And that's what you see happening here. They drill little holes just at a glancing angle into the titanium tip. And that increases the performance of the jet engine by maybe 1 or 2%. And that is economically important. Next slide. Now, we now turn from the brute power of industry to machining on a fine scale. And what you see here is a human hair. And with a pulsed excimer laser, you can drill holes in a human hair. Totally useless. But it illustrates the precision you can obtain with laser beams. In fact, because you can focus them to 1 micron, a laser beam acts like a knife that is much sharper than the best surgical scalpel. The sharpest knife has an edge of about 10 microns. Laser beam is 10 times sharper. And it can be easily controlled by little mirrors to where you want it. You don't have a slightly shaking hand. And not only that, then you cut a blood vessel with such a laser knife, and you don't have blood loss, because automatically the 2 sides of the artery or vein you have cut are cauterized by the heat, and so laser surgery is much more precise and much more clean than knife surgery in most cases. So this brings us to medical applications of lasers. Next slide. Here you see an ordinary light bulb produces an image on your retina. You don't have to worry. But if you look into a laser beam, don't do it. Because that light gets focused so sharply, the light goes through, of course, the lens and the material in the eyeball. But out here, if it's blue or green, it gets strongly absorbed by the red blood vessels in your retina. And you burn a hole there. Now, that's not useful, but burning holes in the retina is very useful if you don't do it at the spots of sharp vision, the fovea, but do it here. Next slide. And that is used to repair tears in the retina. And here is this patient in doctor's office. You don't have to go to the hospital. This is an argon ion laser. The doctor looks where the beam points and then shoots. And what happens, next slide, is that you produce scar tissue. You have burned the retina at all these white dots. And then scar tissue grows back and reattaches the retina, which was loose by this tear. So it's just like sewing two pieces together. That's retinal reattachment. And it was not the earliest surgery, laser surgery, and not very sophisticated, as you can see in a way. Next slide. This is the forehead of an 80-year-old man who his whole life had to wear his birthmark, which was a port wine stain, big red spot in your face elsewhere. And this used to be inoperable. But at 80 years old, next slide, this man was cured. And there is his forehead when he was 81 years old. Next slide. What happens is the following. That the doctors shine a laser beam on it of just the right duration and the right intensity. And then the red comes because parts of the skin, microscopic parts, have too many blood vessels. But in between, there is normal skin. And now, if you put the laser beam on, that gets more absorbed by the red parts than by the normal parts. So the temperature in the red part rises more than it rises there. And you raise it so much that just like boiling an egg, you denature the protein, the so-called coagulation temperature, about 70 degrees. And if you go above that, those cells die. So the cells in the parts of the skin that were too red die, while the parts that were not red are saved and then grow and expand. And that is how port wine stains are treated. It works. You only have to do it with a laser of the right wavelengths and the right duration and the right intensity. Lasers are used very frequently now to sculpt the cornea so that you don't have to wear glasses. And you just have a computer-controlled thing and you reshape the outer surface of the cornea. Next slide. You can also get light into the body by optical fibers, of course, and you insert them into an artery, and you can even get them inside your heart. And that has been done for people who had poor blood flow into the heart muscle. Now, what they did then is drill holes, not through the heart wall completely, but halfway through. And then the body tries to reduce that damage by adding new blood vessels, and so you get a new supply of arteries to get more oxygen to your heart muscle. That works. What hasn't worked yet in practice is to remove plaque from your coronary artery. I mean, it's easy to remove the plaque, but it's very difficult to do it without also drilling a hole in the artery wall, and then you would have a fatal leak. And therefore that application still needs much further work for it to work. Well, this I hope I've shown you that most of these laser applications have been beneficial to mankind. I already mentioned that the big application of defense against intercontinental missiles doesn't work yet, and if it is going to work at all, it's probably will not be done by lasers anyway. But there are good applications of lasers in the military, and every tank, be it an Iraqi tank or a US tank or a Thai tank for that matter, have a laser rangefinder. That they have a ruby or a neodymium glass pulse. They shine it out to the target. They measure the scattered light coming back, which they can do because it's a very definite wavelength. And then they know how long it took for that light pulse to go back and forth. And then they know the range to the target. And also lasers are used, very importantly, widespread, for target designation. That you have troops on the ground and they hold a little laser and they know the wavelengths. And they shine it on, say, a bridge or whatever the target is. And then a pilot has a detector which only detects the scattered radiation back at that particular frequency, which you see. And then he can home into that, or you have a smart guided missile who looks at that radiation coming back from the designated target. And the question always is any military application good or bad? And some people say they're all bad. But in this case, it had saved a lot of civilian lives. There's a famous example of the bridge in Vietnam during the Vietnam War, which was missed 10 times and destroyed adjacent farmhouses. And then for the first time they used a laser designator, and then the bridge was hit right away without causing civilian damage. So in conclusion, the last slide shows you, no, that's backward, too forward. Yeah, I hope you can see this. There are two curves, a red curve, which is the laser sales, and the blue curve, which is the computer sales market. And they coincide because we have eliminated a 70-year difference in development. The computers, of course, were the first. Transistor right after World War II. Laser came later. But you see, these two fields of computer and laser have a very similar history, albeit with a 17-year delay. And this slide was published in 83. And that is for the red curve. So the blue curve could go on till the 80s, 82. But the red curve had to stop here. But then you could predict, if this analogy holds, where the laser market would be later. And in the year 2004, the laser market should be about where the computer market was 17 years ago in 86. And that is about right. That's between 10 and $20 billion. So this is rough, but I'm surprised that economists had the guts to propose this, but it seems to hold. And so that is a very substantial economic market, and it's good to remember that more than 80% of that is for civilian purposes and less than 20% for the military. Thank you. Can you push it one more? Otherwise I use that slide. Before we push the forward. Push it forward one more. Before you take it out, push it forward. Push it forward, otherwise that slide won't come out.
I think we all appreciate Professor Nicolaas's lecture. Now is the time for the questions. If you have any question, you may put the question in the pieces of paper that we gave you, or you can use the microphone from, just raise your hand and Kun Chitima will give the microphone to you. นะครับก็ขอเชิญนะครับทุกท่านถามคำถามได้เลยตอนนี้นะครับเป็นภาษาไทยก็ได้นะครับเดี๋ยวจะแปลให้เป็นภาษาอังกฤษคุณจิตติมาครับ
Professor, would you please mention a little bit about the strategic Star War that you have been involved in that project that have been that involved in the laser technology. So would you please mention a little bit in that project, please?
Well, we analyzed the problem of directed energy weapons proposed for use in Star War in the late 80s. And we concluded that it was beyond the technological capabilities at that time, and we said even if you look forward 10 years, it won't happen. And now it's already 20 years past that time, and it still hasn't happened. It is just the strategic defense initiative promoted by President Reagan never produced a strategic defense. But it is even worse than that. Now we don't talk about strategic defense because the Soviet power has diminished. Now we talk about a single incoming intercontinental missile in terms of hundreds or thousands of them at the same time. And even that we cannot do yet. It is an extremely challenging problem, and technologies that may provide that ballistic missile defense are probably not the laser technologies.
Thank you, Professor. I have two questions actually. The first one is about the incredible laser. Would it be happen in the near future? You said it won't happen now, but it will happen in the near future. So
What?
the incredible laser.
No, won't happen in the near future either.
Okay. And another question.
It would take at least another 10 years.
Right.
And even that is doubtful. I think the people will decide that you need other means for anti-missile defense.
Right, that's the big one. For another one, how about a portable, weapon that could, the soldier could carry around with lasers and things like that? Is that possible?
Well, you can carry a laser around, but what would you like to do with it?
No, I mean to destroy instead of the gun or something, you can carry lasers.
No.
Fiction.
Look, you can make a fire, you set fires with a laser beam very easily.
Right.
But
I can't carry carbon
look,
dioxide.
if you want to set fire to an enemy city, use fire bombs. Don't use a laser.
Right. So it's impossible to carry the carbon dioxide laser, very high power, around with you?
No, very high power laser you cannot carry around with you.
Okay. Thank you very much.
Other questions?
Professor, it's a very interesting talk. One question I have is, you say you can look at ordinary light and your eyes wouldn't be affected. But if you look at laser light, then you're talking something more dangerous. How dangerous?
But if you look directly into the beam,
right.
If you look at reflected, scattered laser light, it's safe.
Right. But how dangerous is ordinary laser gadget, like the laser pointer, for example?
Like this one here?
Right, like that one there. Can you look into...
That is so low power, you probably could look into it.
Oh, okay, so...
But why would you do it? It's not a pleasant sensation.
Okay. Thank you.
คำถามอื่นไหมครับใส่เสร็จกระดาษก็ได้นะครับที่ให้ไปเมื่อตอนต้นชั่วโมงนะครับขอเชิญเลยฮะยกมือแล้วก็ยื่นได้เลยนะฮะมีไหมฮะยกมือเลยครับนะครับเพื่อประหยัดเวลานะครับยกมือได้เลยมีไหมฮะคุณจิตติมาพร้อมที่จะรับคำถามจากคุณนะครับเอาเลยครับนักเรียนก็ได้นะฮะเป็นนักเรียนบ้างเชิญครับ
One back there.
คำถามอื่นก็ยกมือได้นะครับนะฮะเจอเลยนะครับ
Yes, this one is working. Professor Bloembergen, I have a question for you which is a little bit further than only technical matters and lasers. I mean, in your life, you have worked with lasers and masers and high technology, and you have often probably been in that position. Should I work on the military line or on the civil line? Is this one of the reasons that you are still at the moment trying to bring peace in the world by giving lectures to young people?
Well, I never hesitated to accept money for my research from military agencies. And the point of my lecture is this, that even though the military may be the first to push new developments, it may turn out in the end that most of these developments are more beneficial than harmful for mankind. And I've worked in two fields, magnetic resonance, which was also supported by military agencies for other reasons. But eventually it led to MRI, enormous application of nuclear magnetic resonance, leading to a new medical, very widespread diagnostic technique. I've been told by some medical doctors that this is just as important as X-ray diagnosis. So that is one thing. And then in my talk, translations have been distributed. I point out that even things that were very powerful militarily, and those were the airplanes in the First World War and the jet planes in the Second World War. Now everybody is happy we have airplanes so we can move fast from one city in Thailand to the next. So, and the biggest of all is the World Wide Web, which was really started as the ARPANET, the requirement of the Advanced Research Project Agency of the United States Department of Defense, which led to the World Wide Web. So you shouldn't judge too soon what you're working on and who funds it.
โอเคนะครับก็ท่านได้กล่าวถึงว่าจริงๆแล้วในทางด้านสงครามนี่ยังใช้น้อยอยู่ใช่ไหมครับจะใช้ในทางด้านการประยุกต์ซะมากกว่าเช่นเครื่องบินหรือว่า World Wide Web ใช่ไหมฮะแล้วก็เวลาที่จะประยุกต์ใช้นี่ก็คงจะไม่ใช่ว่าใช้เวลาสั้นนักคงใช้เวลาระยะหนึ่งถูกไหมครับนะฮะโอเคนะครับสำหรับคำถามจากฟลอร์นะครับที่เป็นนักเรียนบอกว่าในการรักษาร่างกายโดยใช้เลเซอร์ใช้ในการรักษาโรคอะไรบ้างและทำอย่างไรนะครับ The question is to cure the disease of human body by laser. To cure the diseases of human body by laser. What diseases can be cured and how?
I don't quite question. What is the implication of the question? There are lots of types of laser surgery that can be done.
Okay. Are there special diseases that can be killed by laser?
Yeah, if you have a cancerous growth on your vocal cords, very hard to do with a surgical knife, so you use a laser beam. Okay. If you have cancer in the ovaries of a woman, often laser lights are used for that. If you have stones, kidney stones, they can be destroyed by laser beams. And there is a journal comes out every month, and I think there is more than one, but I know the one that comes out by the Medical Laser Society in the United States. And there are discussions of new laser procedures all the time. this will be bring more improvement to medical science in the next decade.
ครับคำตอบก็คือเวลาเน้นนี่ก็คงจะไม่ได้เน้นว่าเป็นโรคไหนเป็นพิเศษนะครับแต่ว่ารักษาได้หลายโรคเนื่องจากว่าเวลาทำการผ่าตัดเนี่ยสามารถที่จะฉายลงไปบนที่ special area พื้นที่เล็กๆนะครับก็ทำให้การรักษาเนี่ยทำได้ดียิ่งขึ้นนะครับซึ่งท่านยกตัวอย่างในเรื่องของมะเร็งรังไข่แล้วก็อาจจะเป็นนิ่วที่ในกระเพาะปัสสาวะอะไรแบบนี้ซึ่งต้องการผ่าตัดที่ละเอียดมากๆก็สามารถจะใช้เลเซอร์ได้แล้วก็ถ้านักเรียนสนใจก็สามารถที่จะดูจากวารสารของทางด้านการแพทย์ซึ่งมีออกมาทุกเดือนมีงานเกี่ยวกับทางด้านเลเซอร์นี่เยอะแยะเลยนะครับครับ The next question is what kind of source used to produce the laser now
What kind of
source source
What kind of source
used to produce the laser now?
Well, there are hundreds kinds of lasers, and I've shown you gas lasers and solid-state lasers, CO2 lasers. Huh? No, there's not. They are popular for different purposes. So there are many popular ones. The most popular one are the semiconductor lasers. And 2/3 of, so about 4 billion is used for semiconductor lasers because they last a long time and they replace most gas lasers and they are most widespread use are the semiconductor lasers.
ครับแล้วนะครับในยุคปัจจุบันนี้ก็มีใช้เลเซอร์ทุกชนิดเพราะว่าใช้ในการประยุกต์คนละแบบกันนึกออกไหมครับแต่ว่าถ้ากล่าวถึงโดยทั่วไปแล้วที่ใช้เยอะก็คือเซมิคอนดักเตอร์นะครับเซมิคอนดักเตอร์เลเซอร์ซึ่งเหตุผลก็คือเนื่องจากใช้ได้นานกว่านะครับ
ใช่ครับมีคำถามครับ Could you please tell me your work philosophy what make you so successful
Look well look if you want to do research, you have to be curious, inquisitive, and you have to pose yourself a certain question, and you are determined to find the answer. That's the first requirement. And then it is like in sports, it's 1% inspiration and 99% perspiration.
นะครับท่านก็ได้ให้ปรัชญาที่ดีกับพวกเรานะครับก็คือว่ามีปัญหาทางด้านการวิจัยก็คือต้องอุทิศตัวให้กับปัญหานั้นเพื่อที่จะหาคำตอบนะครับนั่นคือเป็นเรียกว่าวิธีการทางวิทยาศาสตร์ทั่วไปนะครับแล้วก็ที่ท่านได้พูดอะไรนะครับที่ให้สนุกมากก็คือว่าจริงๆแล้วงานไม่ใช่เรื่องง่ายเพราะว่าอาจจะมีกำลังใจแค่เพียง 1% ที่เหลือ 99% ก็คืออยากเหนือและแรงกายนะครับ Okay the next question is let me see this one Okay, this is the question from the teacher, I guess, because they would like to know how to solve the problem of short-sighted by lasers. Short-sighted.
To do what by lasers?
ใช่ไหมครับ the LASIK technology.
What kind of technology?
The technology to use the laser to solve the problem of short-sighted, yeah. Short-sighted eyes.
The eyes?
Yeah, for the eyes.
Well, there are various different kinds of eye surgery. I discussed in detail the reattachments of retinas. I mentioned the sculpting of the eyeball. Now, is the question, can you treat other... Yeah, probably if you had a cancer in the retina, you could remove that by a laser beam. But, I mean, I'm not a medical doctor. I mean, there are many eye surgery procedures I don't know about.
โอเคนะครับจริงๆท่านศาสตราจารย์ก็ได้บอกแล้วนะครับคือจริงๆแล้วเราใช้แสงที่บรรยายไปใช้แสงที่ทำให้เกิดเป็นรอยขึ้นมาที่ด้านหลังของตาแล้วก็จากนั้นเซลล์ก็สามารถที่จะ สร้างขึ้นมาใหม่ได้นะครับทีนี้เนื่องจากท่านได้บอกไปแล้วท่านก็เลยว่าเลยไม่ค่อยเข้าใจคำถามนิดนึงแต่ว่าถ้าหากว่าเรื่องอื่นๆเนี่ยท่านคิดว่าน่าจะสามารถที่จะรักษาสิ่งอื่นๆที่เกี่ยวข้องกับดวงตาได้ด้วยนะครับอาจจะเป็นมะเร็งหรือแบบนี้ฮะนะครับแต่ว่าจริงๆถ้าพูดถึงว่าทำได้อย่างไรนะครับเนื่องจากตัวนี้ก็ค่อนข้างจะเป็นที่นิยมก็ได้บอกไปแล้วนะครับที่ในการบรรยายนะครับเอาละครับ a lot of questions here the next one how do we measure the distance between Thailand and USA and if I point the laser to the east or to the west laser will be received at USA or it goes through the atmosphere into the space.
Well, the best way to do it is you would point your telescope in Thailand to the retroreflectors on the moon and then do triangulation.
โอเคนะครับคำถามก็คือว่าจะส่งเลเซอร์นะครับหรือว่าวัดระยะทางจากประเทศไทยไปอเมริกาได้ไงก็คือส่งเลเซอร์ไปที่ดวงจันทร์แล้วก็สะท้อนลงมาได้นะครับโอเคนะครับ I think this is very interesting question what is the most dangerous view of laser the most dangerous view of laser the most dangerous aspect
The most
dangerous I mean what is the most harmful effect of the lasers
the most harmful?
Yes for the lasers
Well, the most harmful effect that can occur and has occurred is to look directly into a laser beam and be blinded in that eye. But of course, if you had a very high power lasers, you could evaporate. You could be burned completely.
ครับอัน
So
นี้
you know, if you have a very high power laser beam, you shouldn't walk into it.
ครับ
But I mean, the chances are that small because these high power lasers are only used in industrial manufacture and they are well shielded, so that you shouldn't walk through a CO2 laser beam of 30 kilowatts. You would burn up. You would boil in a very short time. So, but before that, you would probably get blisters and jump out.
ครับผมก็ได้ถามถึงจากคำถามจากฟลอร์ที่ว่าเลเซอร์มีอันตรายมากที่สุดตรงไหนนะครับท่านก็ได้บอกว่าจริงๆแล้วส่วนที่อันตรายเนื่องจากว่ามันเป็นอะไรนะเป็นสิ่งที่มีพละกำลังสูงมากนะครับมีกำลังสูงมากเพราะฉะนั้นถ้าหากว่าจ้องโดยตรงหรืออะไรแบบนี้นะฮะหรือว่าผ่านโดยตรงก็อาจจะมีอันตรายได้นะครับสืบเนื่องจากพลังสูงตรงนั้นนะครับทีนี้จะมีคำถามเยอะเลยเดี๋ยวให้อาจารย์นะครับอาจารย์พัทระช่วยสกรีนหน่อยนะครับเพราะว่าอย่างบางคนถามมาว่าใช้เลเซอร์ในการเล่นซีดียังไงนี่จริงๆนี่สามารถที่จะหาข้อมูลได้ง่ายมากเลยนะครับก็ขออนุญาตผ่านคำถามนั้นไปนะครับอันนี้ก็น่าสนใจนะครับ which material that laser cannot go through
There is none. Laser can go through any material. Lasers are used to drill holes in diamond. Now, why would you want to drill a hole in a diamond? Very wide use in the wire drawing industry. If you want to make miles and miles of steel wire, you take steel and you draw it through a diamond hole. And if you want it narrower, you draw it through another diamond. There's a smaller hole. And so drilling in diamond is a very important industrial process. But it shows you that the laser can penetrate any material.
เอาละครับได้คำตอบจากท่านแล้วนะครับก็คือถามว่าอะไรที่เลเซอร์ไม่สามารถจะผ่านได้ท่านบอกไม่มีเลยนั่นนะครับแล้วก็ท่านได้ยกตัวอย่างในกรณีของการที่ใช้แสงผ่านเพชรนะครับสามารถจะผ่านเพชรได้เป็นช่องเล็กๆทีนี้ก็เลยมีคำถามว่าแล้วทำไมถึงต้องไปส่องเพชรด้วยในเมื่อราคาแพงใช่ไหมเอามาติดไว้ที่นิ้วจะดีกว่าใช่ไหมครับความจริงก็สามารถที่จะใช้ดึงเหล็กกล้าให้เป็นเล็กๆได้เป็นลวดเหล็กกล้าเล็กๆได้นะครับโอเคนะครับอันนี้บอกว่าเขาบอกว่าใช้เลเซอร์เปลี่ยนลักษณะพันธุกรรมของพืชได้แล้วถ้าเราใช้เลเซอร์มากๆจะมีโอกาสกลายพันธุ์ไหม Is there a chance that human body or human can be mutated because of laser
A human can detect it?
No mutate mutation.
Very unlikely.
Yeah.
Very unlikely. Because the energy of a light quantum is so low. The mutations come from X-rays, gamma rays.
ครับอันนี้ก็เรียกได้ว่าเป็นคำตอบที่ชัดเจนไปแล้วนะครับก็คือมีโอกาสน้อยมากนะครับในการที่จะทำให้กลายพันธุ์นะครับ Can we produce lasers from all noble gases? From all noble gases?
Well, it's amazing that most elements can be made to lasers.
ครับอันนี้จริงๆสามารถที่จะทำได้จากทุกธาตุนะครับสามารถที่จะทำได้นะครับ Is there are there any applications in astronomy for lasers? Astronomy.
Applications?
Yes.
Yes. The biggest experiment being done is the so-called gravitational wave detectors. The one in the United States called LIGO, a long-distance interference gravity detector. And what you use is a laser beam that goes for 2 miles in this direction and 2 miles in that direction, and you combine them again. And you try to measure displacements of this far-away mirror due to a gravitational wave from a supernova explosion. And there are similar experiments set up in Germany and in Japan, and people hope to detect gravitational radiation that way. Very specific, very important astronomical problem.
ครับก็มีคำถามว่าสามารถที่จะใช้ทางด้านดาราศาสตร์ยังไงบ้างนะครับท่านก็ยกตัวอย่างว่าสามารถที่จะวัดแรงดึงดูดของดาวต่างๆนะครับที่มีผลต่อการเคลื่อนที่ของกระจกสมมุติว่าจากส่องแสงจากดาวหนึ่งมายังกระจกใช่ไหมครับแล้วก็ส่องไปที่อีกมุมหนึ่งนะครับจะดูว่ามีอิทธิพลจากแรงโน้มถ่วงของดาวต่างๆอย่างไรบ้างนะครับอันนี้ก็เป็นอีกการประยุกต์หนึ่งนะครับคำถามสุดท้ายนะครับเป็นคำถาม this is the last one is there a blue laser if there is the process to produce laser is different, isn't it? Could you briefly...
What kind of blue laser? Blue? Oh, there are blue lasers.
There are?
Oh, yes, there are many blue lasers. Blue?
Blue laser.
Oh, yes. There are lasers, not only in the blue, there are lasers in the UV, all the way to the vacuum UV, down to 180 nanometers. And there are even, what people are working on is X-ray lasers. And some have been produced, but that is really still the forefront of research. But there are lasers all the way from microwaves, what they call masers, through the far infrared, the near infrared, the visible, and the near UV and the ultraviolet UV. The X-ray laser is the frontier for the frequencies of lasers.
Are the processes of production the same?
Yeah, they're all the same.
ครับโอเคนะครับก็มีบลูเลเซอร์เยอะแยะมากมายทีเดียวแล้วก็นอกจากนี้ก็จะกระบวนการต่างๆนี้จะเหมือนกันนะครับทีนี้ก็ขออนุญาตเนื่องจากเวลาเราจำกัดเราจะทำไงดีครับอาจารย์ก็จะให้คำถามกับวิทยากรอีกครั้งหนึ่งนะครับแล้วทีนี้นะครับเพราะว่าเวลาเรามีน้อยที่คำถามเรามีเยอะนะครับเราก็จะมอบคำถามให้กับโปรเฟสเซอร์แล้วกันแล้วก็อย่างจะขอความกรุณาให้ใส่เบอร์อีเมลด้วยเผื่อได้มีการติดต่อกันนะฮะอันนี้คิดว่าน่าจะโอเคท่านมีเวลานะครับไม่มีปัญหาใช่ไหมครับโอเคนะครับสืบเนื่องจากเวลาของเราจำกัดนะครับอาจารย์พิพัฒน์คิดว่าที่จริงอยากจะให้ท่านนอกเหนือจากให้ปรัชญาแล้วเนี่ยนะฮะท่านน่าจะมีความคิดอะไรดีๆให้กับนักวิทยาศาสตร์รุ่นใหม่กับพวกเรานะครับ I think for the last minute here you might have some ideas or opinions or inspiration for the young scientists. Could you give that to us, please?
Yeah. You want to? Well, whatever you decide to do, you have to do it with conviction and with enthusiasm. If you cannot find anything in science that elicits your attention, then don't go into science. It's as simple as that. But if you are interested, keep going, because you will certainly find some answers that may interest you.
ท่านก็ได้บอกว่าอย่าเพิ่งเสียกำลังใจนะครับทุกสิ่งทุกอย่างที่คุณกำลังทำอยู่นะครับก็จะมีคำตอบอย่างแน่นอนสำหรับคำถามที่กำลังทำวิจัยกันอยู่นะครับแล้วก็ถ้าสมมติว่าเกิดว่าไม่ได้สนใจก็คงต้องออกจากโลกแห่งวิทยาศาสตร์นี้ไปนะครับได้ให้กำลังใจที่ดีกับพวกเรามากๆเลยเป็นสัจธรรมของทางวิทยาศาสตร์ดังนั้นก็ could we give a hand to Professor please ครับก็ขอกราบขอบพระคุณเป็นอย่างสูงทีเดียวนะครับลำดับต่อไปนะครับก็จะขอกราบเรียนเชิญท่านคณบดีคณะวิทยาศาสตร์นะครับมอบของที่ระลึกครับให้กับท่าน Professor ครับ Next we would like to invite the Dean of Faculty of Science to give the token of appreciation to Professor Nicolaas.
Thank you very much.
ลำดับต่อไปจะขอกราบเรียนเชิญดีอีกครั้งหนึ่งเพื่อสุนทรพจน์ปิดนะครับ We would like to invite the Dean of Faculty of Science for closing speech. Thank you.
Honorable Professor Nicolaas Bloembergen, speaking on behalf of the staff and students of the four conventional university in southern Thailand, Thaksin Warailak Rachapat, especially for our well-established Prince of Songkla University with its 5 campuses in 5 provinces. The representative of the Minister of Interior, of Defense, and of the Education, the local and regional authorities, and all other participants in this room. I, as the Dean of the Faculty of Science, and as a scientist and a nuclear physicist for that, have the honor to thank you, your full heart, for your inspiration lecture delivered here in this pumpkin hall. Your presentation here could not have come at a more appropriate time, having the title Laser Technology in Peace and War. Because the southern part of Thailand, of our peaceful country, experienced in this week outbreak of truth force. Your message to our leader, to our teachers, and to our students come at the right moment. We all now also understand how your career has been shaped in your beloved academic subject, physics, the basic science about energy and power. Several of us realize that having you here and listen to you, that you deep concerned about war and peace is most likely based on your pre-war and wartime experience in that other peaceful country, the Netherlands. Our young students may feel how the traumatic experience of these 10 years interfere with your studies, and while you are still dedicate your energy and intellectual power to bringing peace wherever you go. Those of our students who could not continue their study after the New Year violence and the decree state of martial law in these 3 provinces concerned should feel strengthened by your work, and example of coming as your advanced age, here to encourage them and to their teacher. This is especially valuable for our oldest campus in the town of Pattani, with the honorable name after the father of our true leader, His Majesty King Bhumibol. Moreover, because you certainly spoke from personal experience, having been advisor in the corridor of the highest political power in your second wonderland. Many of us now hope your signal to our political, educational, and religious leaders find open ears. Humanity, social science, religious study, all subjects taught and studied at the Pattani campus shouldn't suffer any longer from the turmoil, explosion, and anger from both sides. 10 years is enough. Use the science and the cultural mechanism developed by the people for the people to solve the problem. Isn't this is the message that Professor Bloembergen, you wanted us to give us, our current religious, educational, and political leader, and to our future leader to know that. To the audience, please join me to thank you, Professor Nicolaas Bloembergen, once again. Thank you for attention.
ครับก็ขอกราบขอบคุณท่านคณบดีเป็นอย่างสูงนะครับลำดับต่อไปก็ขอเชิญทุกท่านนะครับรับประทานเบรกซึ่งก็จะมีทางด้านหน้านะครับไม่ใช่เบรกรถยนต์นะครับเบรกอาหารว่างนะครับอยู่ทางด้านหน้านี้เลยนะครับกราบเรียนเชิญครับแล้วก็ขอขอบคุณที่เข้าร่วมนะครับครับขอข้อมูล